Our next speaker has a passion for making things. There's a long list of his projects on his qrz.com page. It's probably even longer now. Neil G4DBN is the man in question. And on the face of it, to me, his talk today is not for the faint-hearted. Or maybe I'm just being a wuss, Neil.
Well, yes, I think 5 years ago, that was the position I was in. I was fascinated by all this manufacturing stuff that people were doing, and people were making things like this and magic little relay for waveguide, and so now I know how to make things like this. So it's only taken me 5 years, which it seems like a very happy 5 years.
Well, you've got just under an hour to teach us how to do it.
Yep, I think I first got into the amateur radio when I was taught by George Dobbs, G3RJV at school. So it's been a long, interesting journey. I then had a summer job working at AEI Semiconductors when I was 14 years old, and they were teaching me all about quantum mechanics, and I was doing online computing and all stuff in those days. So it was great fun. But anyway, it's really nice to see the goings on at the National Radio Centre, because back in 1975 as a student, I was actually there learning about quantum mechanics and maths and things like that. It's changed a bit since then. Fascinating to see. I've been making things for as long as I can remember in wood, metal, ceramics, stone, plastic. I'm a basket maker. I'm an avid electronic constructor. I've been a top band DXer for, since I first got into radio, really. And I do radio now between 8.27 kilohertz and 122 gigahertz. I go onwards and upwards to 400 terahertz visible light. I'm doing DXing tests by cloud bounce, but I don't really play on the radio much between 2 megs and 1 gig. There's just so much to do on LF, VLF, and microwaves. So I these days I define myself. What I do in life is I'm a maker of things. I create things. Microwaves and machining has sort of taken over my life at the moment, and I'm very, very busy making exciting and interesting things with some very exciting and interesting people.
45 years ago, as an electronic engineering student in a different life and another century, I took a short course in the basics of machining and metrology, taught by Bob Corley and the team at what was then the Post Office Factories Division. My father and several uncles had worked as machinists and inspectors, mostly on gas turbines and turbochargers. All of them advised me very strongly to choose a career path which didn't involve oil, swarf, noise, danger and 6 AM shifts. So I followed my Auntie Val and great uncle Les into the world of electronics instead. Then microprocessors happened and personal computers, and as a result I've wasted the intervening 40 years getting paid to do things to computers instead of real work. I first got into microwave radio in 1974, and of course I asked my dad for help making a 10 GHz micrometer wave meter and a directional coupler and gun source. Exciting times. I migrated LF for a long time after that, rarely operating above 2 MHz. But I got bored of stamp collecting once I was approaching 300 DXCC entities worked on top band. It took me 25 years to realise that I didn't really enjoy talking to random strangers on the radio. I was more of a maker than an operator. It was a big relief to realise that was perfectly fine. 5 years ago I subscribed to Dubus and saw wondrous creations in metal that were full of mystery about how they worked and how they'd been made, and I wanted to play. My father had just died, and as I'd never really talked to him about machining and metrology and didn't know any machinists, I had to turn to YouTube and Twitter to gain an education. I talked at length to wise old metal bashers who all advised me to invest in old cast iron beasts and learn the trade on those rather than buying a shiny Chinese mini lathe. They also told me very firmly that good measurement tools were vital and to expect to spend at least as much on tooling as on machines. Oh, how I scoffed. 4 years later, I had my first article on machined microwave antennas published in Dubus. My mum was very proud. This is the story of how I've had a huge amount of fun turning ideas and theory into functional antennas, filters and other parts. I'm using my newfound modelling, machining and metrology skills with tools that cost about the same as a reasonably fanatical radio amateur would spend on radios and antennas. The tale follows the genesis of the designs, the modelling of electromagnetic performance, mechanical stress and heat flow, material selection and how I turned those ideas in my head into real functional objects, enabling folks who enjoy operating more than I do to have fun on the radio, while I have fun making things. My first purchase was a 1962 Bridgeport milling machine, which weighed about the same as a small car. Second through the door was a 1982 Colchester 1800 lathe. With those two items and a decent micrometer, if civilization ever collapsed I'd be able to rebuild it. I added a horizontal bandsaw and a 14-ton hydraulic press, and I was ready to cut some metal. The first project I tried was a high-power 1296 MHz coaxial low-pass filter. I used the design tool from Dominique F1 FRV to design a 9th order LPF using 7/16 DIN connectors. The design tool runs in Excel and it calculates the end effects, fringing, termination adjustments and even factors in the capacitance of insulating spacers. I had some 3mm copper pipe, so I used that as the core conductor. The diameter of the outer tube was limited by the size of the 7/16 DIN sockets. To keep the tolerances reasonable, I picked a 1.5mm air gap, meaning I needed 25mm discs. After specifying the acceptable ripple and the corner frequency, the dimensions looked reasonable, so I made a CAD model in Fusion 360 just to be totally sure there were no issues with clearances or manufacturability. I used Fusion to create a dimension drawing and disappeared into the new rather empty machine shop and started making chips, turning some brass bar to 25mm OD, facing it off flat, and then drilled and reamed it to 3mm, cutting small countersinks to help control the solder beads and improve wicking. I parted off the first disc about 1 millimetre oversized, then repeated the process for the other 3 discs. Trying to hold a thin brass disc in a lathe chuck or collet is not easy, so I turned the remaining bar stock to 20mm diameter, faced it off, and cut some shallow concentric grooves in the face. A drop of super glue on the machined face of the first disc fixed it firmly in place and left some room for me to measure the thickness. I faced it to the final size, did a very light deburr of the sharp edges and countersunk the central hole as before. A quick toasting from a blowtorch melted the glue and released the finished disc, which I cleaned with superglue solvent then acetone. A swift reface to the block was easier than trying to clean it, and I repeated the operation for the other discs, getting them all within size to better than 10 micrometers using a 1 micrometer resolution Mitutoyo micrometer. I popped them into the mill vise with an end stop and drilled a shallow 2mm diameter hole at 3 points around the periphery of each disc, and then made some aluminium spacer to hold the discs the correct distance apart, applied solder paste to each disc and fired up the blowtorch. After a clean-up I machined the rectangular block to size, drilled and then bored it using a boring bar on the lathe and drilled and tapped the socket mounting holes. It needed a porthole in the underside of the block so I could reach in to solder the pin of the second 7/16 DIN socket. The next job was to fit and trim the 2mm diameter PTFE pips to length using a 1.5mm thick template, shaving the excess with a scalpel. After soldering one socket to the end of the centre conductor and filing away the excess solder, the next step was to poke a soldering iron through the porthole and solder the pin to the tube. Making that dished plug for the porthole was more work than the entire body, but hey, I'm doing this for fun. I tested the low pass filter using my HP signal generator, directional coupler, reference load and spectrum analyzer. But since low cost VNAs had become available, I used my pocket VNA to check the results. More recently I bought a Nano VNA V2+4, which is much faster to calibrate than the pocket VNA. The match between the location of the zeros and corner frequencies between QUX, the SpecAn and VNA results are pretty reasonable, so I think my machining must have been up to spec. I needed a combiner for a pair of 250 watt amplifiers on 23 SEMs. Making an air dielectric rat race hybrid seemed a great idea at the time. I used ATLC2 to model the surge impedance of a round inner conductor at the centre of a hollow rectangular outer conductor. The program takes an arbitrary bitmap image as input, using the colour of the pixels to define which part of the cross-section is a conductor or air or dielectric and what connects to what. I was aiming for 70.71 ohms with a 10mm copper ring, setting a fixed vertical dimension and varying the width to get the match. I machined the body and lid and turned a joining plug for the ring. After cutting the ring precisely to length and soldering the joint, I checked its circularity on a tapered mandrel. Tapered sleeves reduced the mismatch at each port, and I supported the ring with U-shaped aluminium spacers and soldered all the joints. Drilling, tapping and counterboring all those holes for the lid was kind of relaxing. Testing showed the return loss was a worst case of 19 dB and interport isolation was over 30 dB, with a balance between the two ports of around 1.2 dB. Not brilliant, but then this was more like plumbing than precision engineering. Now I needed a few more amplifiers, so I ordered some 4" by 1/2" copper bar to make myself a few heat spreaders. But when the invoice arrived with a heavy thump in my inbox, I realised I'd bought 4 meters instead of 1. The bar weighed 42 kilograms and cost the thick end of £450. I decided to recoup that by making some DF9IC spreaders for sale. So far I've shipped about 50 of those spreaders and still have a dozen more to finish. I'm almost through my 3rd copper bar now. I had a steep learning curve with machining copper. Snapping an M3 tap is far too easy in nasty, gummy, grabby C101 copper. I migrated to thread forming taps and found some really good tapping compound. Snap taps are now a rare event and usually from carelessness. Face milling was even more challenging. C101 galls and tears as you machine it, and it cold welds to cutters. Horrible stuff. I tried all sorts of techniques with fly cutters and shell mills, but I've settled on a trick I saw on YouTube. A 7-bladed 80mm face mill fitted with a single positive rate polished radius carbide insert. By careful choice of cutting insert geometry, spindle speed, feed rate, lubrication and adjusting the slideways, Gibbs and lead screws nuts to perfection, I'm now able to get a reasonable finish on copper. Moving to C111 free machining copper has helped a lot, although it's a lot more expensive than the gummy stuff. Wholesale copper prices are now more than double what they were in 2017 and the retail cost has almost trebled. More orders for heat spreaders followed, with W6 PQL models being popular, but also some specials for tiny 5.7 GHz devices, a 3.5 GHz unit with M1.6 screws and some high power dummy load mounts. This is a 5.7 GHz masthead transfer to PA system I built in a steel powder coated enclosure. To get effective cooling to the outside of the case, I machined a rectangular opening in the back panel, then fly cut the surface of an aluminium plate, milling a raised area of exactly the right height to fit through the hole and end up flush with the back face. A flat plate bolts into blind holes in the porthole plate to prevent leaks, and the mating faces of the aluminium have a smear of heat transfer compound. The outer parts in contact with the steel are coated with a clear neutral set sanitary silicone, and the whole sandwich was nipped up to a low torque, left for a couple of days and then tightened. I have to be careful to maintain the heatsink above the dew point so I don't get condensation inside the case from the very efficient cold bridge this creates. There's a Gore-Tex breather in the case wall and I flood it with argon each time I close the lid. A container with zeolite desiccated granules inside the case keeps things dry, but the thermostatic control is also a useful protection. I made a few dedicated clamps for this build. These days I'd probably just 3D print them, but I didn't have a printer then. Over the last few years I've made a lot of antenna mounting hardware, things like elevation drives for dishes and EME Yagis, bracing rods for dish feed points, custom quick detach mounts, anti-rotation clamps, and even a through mesh porthole for feeders in a dish. Getting the stiffness and precision required for EME elevation drives sometimes needs bronze bushes and grease nipples, but I try to stick to ultra high molecular weight polyethylene for bushes, as it doesn't need lubrication, it's more wear resistant than steel and has less friction than PTFE. One of the first elevation drives I made was for my own 10 GHz dish. I used a hugely over-engineered elevation actuator that I happen to have, and I made close-fitting clamps and clevis attachments for it. The mast clamps are made by inserting a spacer between two aluminium blocks, then drilling and boring the mast hole. Once the spacer is discarded, the two halves fit very closely to the mast, so there is no risk of crushing or slippage. I usually cut a fine taper on the edge of each curved face to avoid having a stress riser or any pinching. Where a clamp's going to be in place for years, I usually just use gap-filling Loctite to protect the stainless steel hardware in the aluminium threads. But where the bolts need to be refastened regularly in aluminium, I use helicoil inserts or use nuts on the bolts instead of threading the holes. For larger dishes and Yagi arrays, a rather stiffer knuckle arrangement's needed. The torques can be significant and a wider stance is needed to ensure that the mounts can transfer the loads without risk of distortion or fracture. This arrangement is for a 2.4 metre mesh dish which is used on a large pneumatic mast mounted on a van. Counterweights can be added to the rear of the saddle to balance heavy feeds. The bearings are UHMWPE in aluminium carriers with a stainless steel shaft which fixes through a machined knuckle. I added dimples to the shaft so it could be locked in place with grub screws. The saddle assembly side cheeks were milled from 10mm aluminium plate, and the front sections are rectangular extrusion with 6mm wall thickness. The whole saddle assembly is TIG welded. Being able to weld stainless steel, aluminium and even copper has been a revelation, but I'm still terrible at it. So few of my welded creations ever see daylight. Most of the time I machine off the uglies from the outside, but with practice I'm getting better. I made a rotary welding fixture to hold round things and turn them slowly, so I could maintain a perfect angle and torch separation, but I'm still rubbish at welding. Give it a few years and I might be half competent. Carbon fibre tube is excellent stuff for bracing, but needs care with fixing to prevent it failing from excessive crushing forces. I tend to machine terminals from stainless or aluminium with a slight chamfer on the socket and fit a pin in the core of the tube, gluing the whole assembly with a suitable epoxy or acrylic adhesive. These rods were to support a feed horn on a top-fed offset dish. These were a 3-point quick detach fitting for a large mesh dish with a coarse brass thread, and these are to support a 13cm Yagi above a VHF beam. Sometimes carbon can't be used, like where it's aligned with the E field of an antenna. GRP is then sometimes the best solution, but it's also somewhat fragile. I often get asked to machine anti-crush plugs to go in the end of even thick-walled GRP tube, along with split collars which spread the load of U-bolts and similar small area fixings, really designed to clamp metal tubes. Standard size tubes are rarely the correct bore or wall thickness, so they need a lot of machining to get the right balance of stiffness and weight. Smaller bore GRP works best with precision grips and anti-crush plugs. Sometimes anti-split collars made from engineering plastic are needed and can be pinned in place. I made some drilling guides for the collars on one system so the op could fit and drill the collars themselves. Hinge plates for elevation of Yagi arrays present some amusing challenges. I made this one recently. It uses bronze bushes which were made from a lump of bronze given to my father in the 1940s. The bronze was already old by then. He got it from an ancient colleague who was retiring, having worked for the firm since Edward VII was on the throne. My dad used it as a soft anvil. I hope he'd be happy to know it now has a new life, helping to workstations on 70SEM EME. The bushes are split and pinned with a void between them where grease is injected. I had a lot of fun making all the fiddly bits for this mechanism. Various friends had asked me about making 6 and 9cm feed horns, so I decided I'd better learn how to use OpenEMS to do some modelling of the performance of chokes, the variation with tube diameter, and the effects of pin position, size and shape. The first design was a straight lift from the W1GHZ antenna book. A Super VE4MA with a 0.71 lambda bore and almost flat face. I rolled the choke using a slip roller, cut the choke disc, then welded the whole thing together using AC TIG and a filler rod. I machined the block for the end socket with a curved face to mate exactly with the outside diameter of the horn tube. That was how shall I say this, fun. The back short was a turned bit of 5mm aluminium plate with a nice chamfer at the joint to ensure good weld penetration. Once it was all welded and my terrible TIG work was machined off and erased from history, I drilled, reamed and tapped the end socket holes, and after a deburr and polish, it was ready to go. I didn't fit a tuning screw as I had total faith in my filing skills. I managed to stop filing the pin at just the right time, for once. The horn worked well until a minor disaster when it broke the fall of a 1.2 metre solid dish and developed a bit of a fold. Rather than scrapping it, I donated another 6cm horn I'd made to the owner and used persuasion, flames, violence and rollers to get the squished one back into shape. Amazingly, it was still showing a nice return loss dip at 5760 MHz after all of that excitement. It's now back in use by another operator. Not having learned my lesson, I embarked on a few 3.4 GHz feed horns next. On one of them I used a commercial C-band scalar choke, but that was for a 2.4 metre prime focus dish where feed blockage wasn't much of an issue, and also for a 1.2 metre offset where the blockage was reduced compared with what it would have been on a small prime focus dish, for example. OpenEMS lets me model the pattern with a given diameter and different choke sizes to illuminate specific prime focus and offset dishes with a suitable edge taper. OpenEMS seems to work well once you understand the way it thinks about the world and meshes and ports. It's certainly not as functional as the hugely expensive commercial EM solvers, but there are few limits on model size so long as you have a big enough computer, and it is of course free. Once I had a model that worked, I drew them up in Fusion 360, mainly to simplify getting a dimension drawing again. There are benefits to CAD even for those of us who don't have CNC machines. Yet. As for the 9cm horns, I TIG welded the back shorts as usual, but after a bit of a nightmare while rolling and welding the choke on the first one, I decided it would cost very little more to turn the choke from a short length of round bar and fit a clamp collar so the choke could be moved. More importantly, it wouldn't need any of my terrible welding. One day I'll get good enough at welding to be able to show my work without erasing the evidence using the metalworking equivalent of Photoshop. As 9cm band horns are generally too large to fit any normal LNB clamp, I often end up spending as much time making clamps and mounts as I do when making the feed horns themselves. Where a 9cm horn's been used for portable work, I usually machine up a radome cover from HDPE bar. This changes the tuning and match, so these days I include the radome in the OpenEMS model. Turning a 70mm HDPE bar to 1mm or so thickness is an amusing challenge, involving a custom mandrel and double-sided tape. To make that process easier, I'm working on a vacuum chuck using a very clever vacuum generator. You blow compressed air through a small jet orifice and it entrains the surrounding air, pulling a decent vacuum which will hold thin work pieces against a machined face with tiny holes and grooves, and a rotating vacuum seal on the other end of the lathe headstock. The vacuum these things generate isn't high, but should give me at least 12 psi or 80 kilopascals different, so a 70mm workpiece will be held with the force of around 300 newtons, or almost 70 pounds force against the chuck face. The model I use can pull around 0.3 litres per second, so with an internal chuck volume of less than 100 millilitres, the suction reaches maximum in well under a second. One of the other applications of the vacuum chucks will be to hold thin polystyrene and HDPE discs about 200mm diameter, which I'll machine into Fresnel zone plate dielectric lens antennas for the higher millimetre-wave bands, but I'll talk about that in a different lecture. After reading Geoffrey Portland's article in Dubus about short high-performance 10 GHz waveguide feed horns, I decided to have a go at making some for myself to Geoffrey's designs. The thickness of the oval iris plate is specified to the nearest 10,000th of an inch, and the other dimensions are fairly critical, but it worked very well and is still my primary feed on 3cm. I made a few more for amateurs in France, and at least one of them is now being used to work 10 GHz moonbounce. After the success with the WA6 KBL horns, I was asked to make some dual band antennas for QO100 to the Poti design by Mike, Paul and Remco. I made some jigs and cut the parts on the lathe and mill, soldered them up with a machined spacer and made a machined ring for an LNB dielectric lens. It tuned up nicely with the expected dual dip in return loss at plus or minus 40 MHz as the patch was excited in orthogonal modes with a 90-degree phase difference for circular polarization on 2.4 gig transmit. I even made a couple of contacts via the satellite before losing interest and going back to making stuff. After reading another Dubus article by Andrew VK3CV about the 122 GHz transceiver based on a car radar chip, I had a close look at the antenna designs that Andrew had come up with and decided to try some alternatives for folks who wanted to use flattish dishes with a large FD ratio or very deep dishes. My first attempt was a replication of Andrew's feed horn design, but instead of using a shaft and grub screw, I cut a very fine pitch thread into the horn and the mount duplexer assembly to make fine adjustments of the size of the duplexer cavity possible. It was quite a challenging project. Andrew's feed horn had a face about 7mm diameter, with 3 grooves cut into the face to form a choke, like the Chaparral design for satellite LNB horns. Machining such tiny slots needed a 2-flute carbide milling cutter, only 0.5mm diameter. Those cutters are designed to spin at 60,000 RPM. That meant making a special purpose high-speed spindle using a 600-watt 3-phase motor and a variable frequency controller. I made it with a dovetail mounting so it would fit on the Aloris style wedge tool post on the lathe. I wrote some MATLAB code to generate the taper angle and length of W2 IMU dual mode horns and ran simulations to check the gain and side lobe suppression. An important aspect of feed horns for microwave dishes is to balance the illumination of the dish surface so that the illumination is maximised, avoiding too much overspill. A good rule of thumb is to aim for 12 dB edge taper, but that also includes the space attenuation that comes from the feed point being further from the dish edges than the centre. Using OpenEMS, it's easy to adjust the parameters of the model to optimise the edge taper and side lobe suppression, although it does take serious computing muscle to do the simulations. The IMUs would illuminate dishes in the FD 0.6 to 0.8 range, more effectively than the ridged choke design that Andrew used. The core waveguide's only 2mm diameter, so I drilled it with a special fast taper 1.9mm long series drill and reamed it to size with a tiny 2mm cobalt HSS reamer. The flared section's only around 4.5mm diameter, with a taper at 27 degrees. I found some sim turn boring bars which were made from solid tungsten carbide and were only 1.7mm across. That meant I could drill the bore roughly to size with a normal drill and then use the boring bar on my lathe to machine the bore exactly to size and then use the compound slide to cut the taper. Using an 800 kilogram lathe to cut these tiny features on parts weighing grams was surprisingly easy, although I had to use a dial gauge on the tool post to ensure I didn't crash the tiny tool into the opposite face as it entered the bore at the end of each cut. I set up a video microscope so I could see what was going on and used precision gauge pins to check the diameter of the outer bore. I've got a set of several hundred of those pins to cover from 0.2 up to 25mm. Edmund Scientific supply low-cost polished deep aluminium dishes with an FD of about 0.25. That makes the focus level with the rim of the dish. To illuminate that, you would need an impossibly wide horn angle. I decided to design a Cassegrain subreflector using the W1GHZ XL calculator sheet. That gave me the coefficients for the hyperbolic curve of the subreflector, which I put into a table to give me a list of coordinates to define the surface shape. Not having a CNC machine, I made a dovetail clamp to fit the cross slide of my lathe and used the XY position table to cut a flat template on my milling machine in tiny manual steps. Then all I had to do was use a round 10mm diameter lathe tool and 10mm round pin to follow the template, and I had an instant copying machine which can reproduce the flat curve as a 3D surface. The trigonometry and calculus involved to work out the shape of the curve is definitely challenging. I really need a CNC machine. The high-gain Pickett-Potter dual-mode horns for 122 GHz needed a different approach from how I made the W2IMUs because of the length of the taper. Once again, I modelled the dimensions using calculated values for the size of the guide, step and outer taper. I decided to make the taper 10 wavelengths long and a 6 wavelength diameter opening. I took a piece of tool steel, machined it to 18mm diameter and then cut the taper on my lathe. After machining it, I used a gas torch to heat it to cherry red and quenched it in oil. That made it glass hard and brittle. So I popped it in the kitchen oven at 220°C for an hour to temper it back to usable hardness. The tapered face needs to have a very fine polish and the edge must be razor sharp. So I use the tool post spindle as a grinder, spinning the D bit in the chuck and using the compound slide to put a fine precision grind on the tapered face. I ground off the tip with a relief angle using my Deckel copy cutter grinder, form the step which stimulates the formation of the second mode in the horn. A final lap of the flat face of the D-bit with a fine aluminium oxide paper and then with diamond dust slurry, and the D-bit was ready to use. The finish it creates on brass is very good straight off the machine, but I still used a tapered Delrin rod with 2000 grit paper to polish any remaining surface imperfections. Once the tape is completed, I use a 3mm silver steel rod in the tailstock to measure the depth of the taper to the step and then machine the face to the final length. After that there's just the outside diameter, outside taper, an M8 by 0.5mm thread and waveguide cavity shaft to machine. The horn fits in the same modular mount and duplexer cavity as all the other 122 GHz parts. I've also made some horns and adjustable flange connectors for 122 GHz, machining UG387U flanges with 440 UNC captive lock screws. I made my own lock screws after finding how expensive they were to import. I had to make a special tool for that as well, plus a holding jig and lantern chuck to trim the threads to length. The flange adapters were quite intricate as the flange is free rotating with a split lock nut, and there's a separate threaded adjustment for the duplexer cavity with its own lock nut. The duplexer body is reamed to 4mm to fit the 3.98mm waveguide shaft and then tapped with 4 M2 holes to mount to the VK3CV boards. Dom F6DRO asked if I could make a biconical dielectric lens for him for a 10 GHz feed horn. I machined a 21mm ID brass tube for the horn body and bought some Rexolite 1422 cross-linked polystyrene dielectric from Specialist Engineering Plastics. It machined very nicely and gave excellent results. Later, Vili HB9PZK modelled a truncated dielectric lens with a step matching section for the Poti, and I made a couple of batches of those. The step section made it much easier to grip the lens in a collet chuck. I've made a few dual band setups using a cluster of single band feed horns, some mounted over and under, some side by side, and it struck me that using dielectric lens feed horns would allow, say, a 5.7 and 10 GHz feed to be mounted much closer than those with chokes, reducing the side lobes and loss of gain you get when a feed isn't exactly aligned along the dish axis. I started with a 5.7 GHz horn, running an OpenEMS model to optimise the electromagnetic design, and then CAD as usual to get the exact dimensions into a drawing. Machining it was challenging, as I wanted to maintain the outside diameter at 40mm to fit the standard LNB clamp. That left the wall thickness at 0.8mm, rather too thin to be machined reliably. More mangled aluminium ended up in the scrap bin. On the third attempt I had a usable body. At that point I decided I should probably make the walls slightly thicker and make a custom clamp, Reducing the inside diameter would compromise the electromagnetic performance too much. The 10 GHz horn went much more smoothly. The first attempt looked good, and after trimming the SMA pin to length at the first attempt, the return loss was acceptable. A quick test on a turntable confirmed that the illumination taper was within spec. I mounted the horn on a spare offset 1 metre dish and aimed it at the sun and then cold sky. It showed around 5 dB of excess noise when beamed at the sun, with a beam width of around 2 degrees. I could probably have squeezed another dB or so out of it by careful adjustment of the position of the lens horn. The next step will be to make a waveguide fed version of the dial spike horn with a tapered transition from WR90 or WR75 rectangular to 21mm circular guide. So, what does the future hold for the DBN machine shop? So far, everything I've been doing has used manual subtractive machining and traditional fabrication techniques. But there are things that I can't do using those methods. CNC machines with the same precision and performance as my old manual clunkers are furiously expensive. So I'm working on CNC add-ons for the Bridgeport and Colchester. That'll take away the stress of cutting the dozens of tiny slots on 24 GHz slot array antennas, and also make it easier to make close-fitting covers for microwave PCBs to help suppress waveguide resonances inside cases. It'll also mean I can machine arbitrary compound curves, aspheric lenses, and make complex 3D shapes from solid. If I ever get better at welding, I now have a giant slip roller to make 23 SEM and 13 SEM choked aluminium feed horns with welded seams and milled stepped polarising septums for large circular polarised feeds on big EME dishes. My biggest EME dish is only 3 metres diameter, tiny really. As for additive machining, I've invested in a Prusa 3D printer for prototyping, as there are now suppliers who will take a CAD file and use laser sintering to make solid metal 3D printed parts. I'll be able to make prototypes in plastic before ordering the metal parts and making expensive mistakes. Another application of the 3D printer is to make casting patterns, so I can make complex parts from molten aluminium or bronze using Petrobond oil-bound sand in a dragon cope and sodium silicate sand hardened with carbon dioxide to make cores for hollow castings. Even fancier castings possible using the ancient lost wax technique, but with a 3D printed positive made from polylactic acid filament. The print's coated in slurry and sand or investment casting plaster, and then the PLA's melted out and vaporised in a kiln. The empty moulds then filled with molten metal, and you're left with a solid cast metal replica of the 3D object. Another 3D print application is using pre-perm dielectric filament to make complex lens horns and dial spike, dial guide antenna feeds. I'm also working on anodizing and electroplating for surface protection and improving surface conductivity. But the most exciting use of chemical deposition, I think, is electroforming. If I want to make an elliptic tapered corrugated feed horn for 47 gigs or higher to get the best possible RF performance, I need to cut very deep, very narrow and very, very precise internal grooves in a tiny horn. All but impossible, especially in copper, which is awful to machine at the best of times. The trick is to machine a negative mandrel with the shape of the inside of the corrugated horn in aluminium, and then etch off the oxide, immerse it in a zincate bath, then straight into a gold electroplating tank with the power on. The zinc layer disappears instantly, leaving bare aluminium, which allows gold to be plated onto the mandrel. That's followed with a plating of silver or nickel, and then a thick copper layer. The outside's machined to size with the mandrel in place for alignment, and then the whole thing's immersed in a hot caustic bath, dissolving the aluminium, leaving behind a gold-plated copper feed horn with those tiny internal corrugations. So that's how I do my amateur radio hobby. I've still got a lifetime of challenges ahead in machining, design, modelling and metrology. Taking my abstract ideas and bringing them to life as physical objects is already enormous fun, but the bonus of being able to use those parts to talk to people on the radio is the icing on the cake.
I'm sure that was metalwork porn to some of our viewers today, Neil, but it confirms to me that I am indeed a wuss. Do you take orders?
Well, I've got a bit of a backlog, to put it very mildly indeed, but yeah, I'm doing a surprising number of parts for people. The thing is that people see the sorts of things that I'm making, and then they go away and they have daft ideas, and they say, "Can you make a?" And so I usually say, "Probably,"
and then have a go.
Yeah.
I used to work in an engineering company myself, and I can still smell the suds if I think about it when I was a youngster. Yes. But I used to order the bits for the lads on the shop floor to work their magic. So and there's been a few comments actually. I'm not sure who only identifies himself as 1-2, but he says amazing engineering there. But I have to be careful how I may have to edit this. It says it looks extremely expensive, shall we say?
Those little horns that I make, I ship off the 122 gigahertz ones. I don't charge anything more than the cost of materials. You know, I'm not doing this for income. So one of those little horns probably cost you about 20 quid, 25 quid, something like that. And
I'm wondering if he thinks it's, setting all that gear up for you.
Yeah,
it cost a lot of money.
If you think something like these little transitions, I don't think it'll focus, but these little transitions, you find them on eBay secondhand for £100. Well, there's what, 15 quid's worth of material in that. But yeah, the cost of machines, I usually say it's about the same as a decent transceiver. You spend maybe £1,500 and you can get yourself a Bridgeport. It weighs more than my wife's car did. And, you know, it's not a hugely expensive thing to get. If you want to get something shiny and new, sky's the limit. You know, you would have to mortgage your house. But there are machines out there, and a lot of the stuff that I've got is secondhand. You know, people have shut down engineering workshops, and suddenly I end up with a load of micrometers or all sorts of measurement tools and things to fit in lathes that really only cost pennies.
Okay, you started all this at the age of 14. There can't be many 14-year-olds today, I don't think, who would be exposed to this in the first place to even take it up. What do you think is going to be the future of engineering like this? I
think that's a bit of a problem, because I remember at school, we did metalworking at school, and I was using lathes and milling machines and shapers and grinders from the age of about 11. It was just the thing that everybody did. Nowadays, though, if you think the way the technology is going, this idea of using metal 3D printing is really quite mature, and although it's fairly expensive, if you want to make 100 of something, it's not that bad.
Of course, you're doing all this because you became attracted to microwaves.
I think reattracted is the right word.
Reattracted. Well, what is it about microwaves that has this fascination for you?
I like the idea that you could lose the antenna because you put it in the wrong pocket and you don't know where it is. And that you've got the same amount of gain as a huge moonbounce antenna that you can hold in your hand. But I think a lot of people are still stuck in the 1970s idea that microwaves, you have to go to the top of a hill with a tripod and get cold and wet. All of my microwave operating is done from home, and I'm doing almost any day of the week, I'm doing 400-kilometer contacts, and I have regular skeds with somebody at 340 kilometers. And we even have, if it's raining, we sometimes have rag chews, 3- and 4-way on FM and D star. So surprising what you can do with microwaves. It's just endlessly fascinating.
Bring on the rain. A couple of comments on the website, on the chat, I should say. G1PPA says, great talk, Neil. Well done, mate. That's from Steve. Cracking talk, Neil, and great skill. Well done. That's Chris G0WUS. And Heptode says, that was joyous. I'm using CNC, so can you recommend the So can recommend the transition. And he wonders, what grades of aluminium are you using? That's GM4 LVW.
Well, it varies. It depends what I can find. Sometimes I buy unknown mystery metal that you see if you go to a traction engine rally or something. And I've got some fantastic 7 Series aluminium alloy that is obviously aerospace alloy, and it's beautiful. But yeah, the stuff you buy off the internet is not brilliant. 6062 and things like that are not superb, but they're cheap.
Yeah. Now, you said you pick up a lot of your stuff secondhand. What sort of place do you get them? I've got a question here. For someone who's been excited by the last 40 minutes, but without their own workshop at home, where's a good place to start?
Ooh, now that's a really tough one. There are lots of maker spaces that have got lathes and milling machines, and they tend to be underused because everybody's going there and using the electronic stuff, and they're using the laser cutters and so on. But if you can find one that's got a milling machine and somebody to explain how to do it without injuring yourself, it's a fantastic resource.
And can you find these things like on the auction sites on the internet and things? Yeah. The machinery.
I would avoid eBay, but there are lots and lots of specialist sellers out there selling second-hand machines. I bought both of mine from both my big machines from somebody that was just advertising. It wasn't an option. They just had they'd taken this machine in and refurbished it and sold it on. I think that big lathe of mine, I could have bought myself for, I don't know, about £1,500. I could have bought myself quite a nice looking Chinese lathe, but instead I get something that weighs 10 times as much, and that's hugely more powerful and much more useful and a lot more accurate. For I think it cost me £1,800 altogether, and that included the shipping. But that was just somebody that I found that did refurbished machines.
And what have you got? A shed or an outhouse, a garage? Where do you keep it?
Yeah, I've got my house was thrown together in 1850, and it used to be a small holding. So it's on one of the estates up here in East Yorkshire, and there's a brick barn attached. So what I did, I got my friend over the road who's a builder to build me a machine shop inside the barn. But yeah, it's tricky, but I do know people who are doing it in basements and bedrooms. You wouldn't want to be splashing the amount of oil I splash about though in your bedroom.
In your bedroom, I wouldn't think so. Oh, we've had a comment from Australia. VK2R8 says, that was amazing, inspiring. Really enjoyed your explanation of your thinking behind each step in making the pieces. It was a very professional presentation, I have to say, Neil, really well done. And another anonymous emailed question, any recommendations for getting started with CAD? Oh, now I found there was a nice loophole with Fusion 360. I used to use Eagle CAD design for PCBs, and it turns out that if you spend £100 on your Eagle license, you get a free copy of Fusion 360 thrown in without any limitations other than you don't get any online rendering and so on. But it's a fantastic bit of code is Fusion 360. The learning curve was nightmarish, absolutely awful. I just could not believe how hard it was to get my Windows infected brain into using something that wasn't really Windows centric again. But it's just stunning. However, there are other ones that people are using. What I'll do is I'll collate a list of all of the things that I'm using and some other stuff, and I'll put them on my website with a link. I was going to ask you about your website. So where will we find that?
g4dbn.uk. Easy enough to remember.
Easy enough to remember. There's lots on there. Oh, well, yeah. That's great. Okay, well, I think that's all the comments we've got. Thank you very much. Now, that was a really tremendous presentation. So thank you. And what's your next project then?
I think the next project, the one I'm working on at the moment, is for a 6-metre EME elevation system. But I've got a few ideas about the 30 terahertz band. So yeah, more about that later. 30 terahertz is absolutely fascinating, but you can use electric fire as the transmitter.
Yes, well, maybe that will be the subject of another convention talk sometime in the future. Thanks very much, Neil. Great to see you.